request you guys to just remind me in the beginning of the class to, press the record button. So just curious, how does it show for you guys? Do you see that the recording is on?
There is a red colored REC tab on the top. We can see if it is recording or not.
Okay. So yeah, so just one of you guys just remind me in case it's not on, okay, in the beginning of the class. All right. So one thing I wanted to tell you about is yesterday, I guess some of you approached Gaurav and asked about the assignment. And there was this question about whether you can use other solvers like OR tools. Okay, so for this, yeah, you are free to use any solver. But the only thing is, you should keep in mind is that some of these packages like OR tools has some of the optimization problems already coded in, like things like network flow, mincut. Those some of these standard problems are already coded in. All it requires you to do is just give the graph. Okay, for example, for network flow problem. So I don't want you to use those kind of packages. I mean, for the simple reason that you will also be coding in other things, right? Like in the future, like if you're going to some industry, you will be involved in formulating problems and actually implementing it. By implementing, I mean like putting in the constraints and objective, giving it to a solver. So if you just invoke an existing optimization problem, that doesn't give you practice. Okay, so you can use these solvers, but as long as you code in the objective and constraints yourself. Otherwise, it just becomes an exercise of feeding the graph and those kind of things. So that's not going to be very useful for you. Okay, so another thing in particular about OR tools, yeah, I don't know if I think it's mainly for linear programs and integer programs. So as best as I know, you don't have support for other types of, optimization problems. Like for example, if you have a QP, I don't think it has support for that. So it's not a very general solver in that sense. Okay, so but other things like Gurobi and some of the MATLAB solvers, those are more general. So yeah, it would be in your best interest to use some of these general packages. But yeah, I leave it to you if you are very much comfortable with OR solver and putting in constraints. That's also fine. Okay. So I'm just curious. So have you used OR tools as part of some other course or some project or something? I don't know who approached Gaurav, but are you guys have you used it for some other project or something else? Is that why you are considering using it? Okay, is anybody in this list considering using OR tools? Guys, I want some response. Okay, Rohit says no, Shashwat says no. Okay, fine. So, okay, I don't know, as long as we don't know who specifically asked. Okay, so anyway, if you were considering, so I hope my what I said answers your question. Um, all right, so let's begin today's class. So I'll just start sharing the screen. Okay, so the screen is visible, right? It should be visible now.
Yes, ma'am.
Okay. So today we will look at some iterative algorithms for unconstrained optimization. So yesterday also we did some iterative schemes, but in particular that was for one-dimensional optimization where the function f involved just a single variable. Okay, so today we look at this general theory and general algorithms in the context of unconstrained optimization. Now, we saw some of these necessary and sufficient conditions. So it is very rare that, in practice, you apply that and get a closed form solution. And that's the reason why people go for these kind of algorithms where, it is applicable to any function. Okay, so any kind of function you want to optimize, it doesn't, even if you don't have a closed form value for the optimal, you can just apply this. So that's why these are very popular, and especially you will also see it being used in fields like machine learning, and even several other fields like OR and so on. Okay, so in general, the way you do an iterative algorithm, the way you design an iterative algorithm is you start with an initial point, okay, and then you frequently update. At you make some updates to this initial point. So you move in some direction. Okay, so you update your xk to xk plus some alpha k dk, where dk is some vector. Okay, and you get a new point xk plus 1. Then again you do this update, and you keep doing this until what point? Until you're somehow happy. Okay, so we will see what this means later. Okay, so in terms of terminologies, xk is what we'll refer to as the current point. So we are always going to be interested in this step of the iterative process. So how do you design this step? So xk is the current point, this one. Now dk is a particular direction in which you are going to move. So xk is like this, and dk is, say, some direction like this. And alpha is called the step size. So it is a number, it's a positive number. So, it's just a fraction of the decay, either a fraction or maybe even 2 times decay. In that case, you will go further. And otherwise, you will, go somewhere up to this point. So this would be some, so alpha decay, right? Alpha k decay. And you would increment it by that, xk plus alpha k decay. Okay, and so xk plus 1, that's how you get it. It's the next point by just adding alpha k dk to xk. Okay, so the idea is you do this in such a way that in the next step, when you compute f of xk plus 1, you decrease the value, the function value, to the extent possible. Okay, so that you can reach the optimum point as quickly as you can. Okay, so this is the idea in these iterative algorithms. Now, all we want to study here is how do you choose this dk, how do you choose this alpha k, and also we talked about, you go on till you're happy. So what is the stopping criteria? When do you stop? Okay, so these are the things that you would design in, in proposing iterative algorithms. So we will look at each of these aspects in this class. Okay, so now before we go on to that, I just want to focus on one thing. So we have alpha k and dk. These are these two numbers here. So why are we having two numbers here? Why are we looking at it separately? Right? So the reason is just this. So I'll just show you some examples, okay, why you want to distinguish between these two parameters. So the thing is, suppose this is a function you want to optimize, and this is your xk, okay. Now, you identified that this is the direction you want to move, towards the right you want to move in order to decrease the function value. Okay, now if you move this much by this arrow here, so if you move this much, you will get this point. So that's a good step that you have taken, and that's fine. But the same direction, if you move very far, you will perhaps hit some point like this. Okay, so then you would have, crossed the optimum point also. And now if you see, the function value is in fact going to be even greater. Okay, so then it's no longer a descent direction, right? It doesn't reduce the function value. Okay, now even if you somehow ensure that the function value reduces, so if you reach only somewhere here, okay, so you move this much, but even then you have just crossed over the optimal point. So that's why that's one of the cases why you need to separately also look at how much you can go. Okay, so that's why you need this alpha k. Now, another use case is something like this, okay? Some function like this, and you're starting at this point, okay? So now, again, you identified that you need to go this way in order to reduce the function value. But suppose you move this much, yeah, you reach only here, okay? So if this is the amount you go, then you are here. And if you see, there is not much of a function decrease, right? You're almost where you are. Okay, but if you go a large deal, if you go by a little more, then you are going to come down somewhere here. So this is a substantial improvement. Okay, so yeah, here also there is an improvement, but perhaps it's not enough. It's too, you're still, in terms of the function objective, I mean, in terms of the function value, you've not made much progress. Okay, so that's why, so these are some of the issues that arise, and that's why you need to look at these two with a separate viewpoint. Okay, so is this clear, these kind of use cases? Does it make sense?
Yes, ma'am.
Okay. Right. Okay, so now let us go into each of these aspects about decay, alpha k, and how do you stop the algorithm. So first, let's get into the choice of this descent direction of decay. Okay, so now what is the key thing you want when you choose a direction? It's you want a decrease. So you're solving a minimization problem, and from where you are currently, you want the function value to decrease. So there's this notion called descent direction, which we formalize. So what it means is that you have an xk here, you're at xk. Now you go in some direction dk. And over here, like there's some range around this, okay, around this function xk. And such that if you move along this dk, the function value reduces. So if you consider, so this is some neighborhood around xk, right? And if you consider a movement along the direction dk within this neighborhood, so for all these points here, the function value will be less than what you had at xk. Okay, so that's just formalized using these notations. So decay is a descent direction at the point xk. If you have some neighborhood, okay, specified by this alpha bar, so this is usually the alpha bar, the radius, right? So such that if as long as you make a positive step, so alpha is within 0 and alpha bar, as long as you have that, the new point that you take, xk plus alpha dk, is less than f of xk. Okay, so I hope this notion is clear what we mean by a descent direction. So just to take an example here, okay, so in this function, so if you go along this direction, you have a descent. Okay, so you have a descent as long as you reach somewhere here, right? So this is the neighborhood. So the alpha bar will be specified by this. Okay, and as long as you're within this region, you are going to get decrease. Okay, now alpha has to be greater than 0. Very clearly you see it here. So if you take a negative value here, if you take a step in this way, the direction itself is going to change, right? So you're going to get the opposite direction. There the function is going to increase. Okay, so that's why this 0 comes in here. Okay, so another piece of an example that I wanted to highlight is this one. So this function here. Okay, so this is a point xk. So now suppose you're going in this direction. So if you fix this as your dk somewhere here, you are going to get a decrease in the function value, right? Because this is where you were, and you went down, you got this. But this is not a descent direction, because for all values in some range around xk, so you need to find some alpha bar. Okay, so that every step, I mean every point you get along this direction dk within this interval, that should be you should get a lower function value. But that doesn't happen with this direction, because immediately if you go a small step you make here, the function value is going to increase. Okay, so that's something you should remember. You should have for every alpha in a small neighborhood around it, you should have a decrease in the function value. So for this case, this is a descent direction, because immediately if you take a small neighborhood around, you're going to have a decrease in the function value. Okay, so this is an example of the neighborhood you choose. Okay, so is this clear? Any questions on this? Does that make sense?
Yes,
You're
ma'am.
quiet. I want some response. Okay, so that says okay. What about the others? Bhavna? No questions, Rohit. Okay, what about Bhavna, Devyani? I don't hear from you guys at all. Okay. Aditi, it's clear. Okay. All right. So please ask if something doesn't make sense. Okay. All right. So, yeah, so this is now that we have formally defined this notion of a descent direction, let's look at what you can do here. Okay. So they look at what are called these gradient methods. Okay. So what gradient methods are is that this decay, this descent direction that you choose, it is chosen based on this value of the gradient at the point xk. Okay, so those methods are quite popular nowadays, and so let's just look at that. Okay, so of course you have to, I mean, have a differentiable function, otherwise you can't compute the gradient. Okay, so now one characterization: when is a direction a descent direction? So we saw this. This is the proper. This is the kind of behavior we wanted from a descent direction. But is there something you can characterize more formally? Okay, so that's what we'll see here. And a direction D such that it makes this, an obtuse angle. So D transpose delta fx. So if you take, you're at xk now, you take the gradient. And if you have the direction D such that when you take the inner product with the gradient, you get a negative value, such a direction is a descent direction. Okay, so what does this mean? So pictorially, like your gradient xk, so this is the point xk, and this is gradient f of xk. So suppose it is along this direction. Now remember, this inner product is just nothing but norm d, norm of gradient f of xk times cos theta, right? So here theta is the angle between d and the gradient vectors. So this is the theta. So it's the cosine of this angle which really dictates whether d can be a descent direction or not. So when we say that d transpose gradient fxk is less than 0, what it means is that these two vectors, they make an obtuse angle with each other. Okay, so the moment you have some d in this region, then it no longer makes an obtuse angle, right? So the cosine value is going to be greater than 0. And so this overall product is going to be greater than 0. Okay, because these are anyway norms and those are non-negative. Okay, so this is the property of the descent direction. It is in sort of, you are kind of moving away from the gradient. Okay, so as long as you have some component in the direction of gradient, you will not improve. Okay, so that's the thing. So in other words, a way to look at it is you have the negative gradient, and if this direction d has a component in this negative gradient, then yeah, this is a descent direction. Okay, so how do you show this, right? That any such direction d will induce a descent. So the way to do that is you take this point xk plus alpha dk. Now this is something I'm sure by now you all recognize this. So this is the f of xk plus alpha times dk transpose gradient plus this of alpha. So this is just the Taylor series approximation at the point xk. Okay. Uh, so now you also know what this means, right? So this O of alpha, if you have something which is O of alpha here, now when you take this term O of alpha by alpha, and with the limit alpha going to 0, this is going to give you a 0 value. Okay, so we also saw this kind of some such steps earlier when we showed the necessary and sufficient conditions. Okay, so what this means is that this is a small o notation. So there is any epsilon you take, this value is going to be less than epsilon for as long as your alpha lies within some alpha bar. Okay, so this absolute value, this is also an important thing. So the absolute value of this term O of alpha by alpha is going to be less than some epsilon for every epsilon. Now in particular, if you take epsilon as this value, dk transpose delta fxk, you're going to also have this as true. Okay, so what this means is that this is the term which dominates. Okay, and now we know that this is less than 0. This is what we are given. So this direction which makes, its dot product with the gradient is less than 0. So this is the one which dominates because the rest of them are, captured by this. So that's the reason, right? So now that's why f of xk plus alpha dk will be dominated by this term, and which is less than 0. Okay, so that's why now this term, if you see, this is what we wanted. So f of xk plus alpha dk is less than fxk. So that's why dk is it's a descent direction. Okay, so does this make sense? Yes, no? Any questions on this proof? I mean, this is very similar to what you saw earlier, but if something is unclear, please do ask. It says it's okay. Okay. What about others? Rajneesh? Rajneesh, you're there? It's clear? Okay. What about the others? Is it clear to you all? Lakshmi, it's clear? It's clear? Okay. Okay. Okay, good. All right. So we have this characterization. So this is an important one which will help us. So whenever you look for a descent direction, you look for a direction which makes a negative dot product with the gradient fxk. Okay. So now another point, if you remember, like we had gone over this in our the preliminary classes. So the direction of maximum increase of f of x at the point xk, that is given by the gradient. Okay, and also the negative of the gradient gives the direction of maximum decrease. Okay, so this is something you should recall. So I'll just give you some directions of how we prove this. It's just to recap. So the rate of change of f in the direction while at xk, that's given by this term, right? D transpose delta fxk. This was actually what we referred to as the directional derivative. Okay, so now this, how does this come? Okay, the rate of change of f in the direction d, that's given by this. That is just an application of chain rule. Okay, so the way you did that was we considered another function g of alpha. Okay, so xk and dk, this is given to you, and the only parameter here is now alpha. So the function of xk plus alpha dk that you take. Now, if you take the derivative with respect to alpha, okay, so you can do that by applying chain rule. Okay, so it just becomes this. You take the gradient first, and now you take whatever is there inside in terms of alpha. So that is going to give you a gradient transpose dk. Okay, so these norms are there just to ensure that you have a unit direction. Okay, so now this is the derivative, the derivative of g with respect to alpha, and so the rate of change of f. So if you take alpha for different values of alpha, you're going to get different values of the derivative. So the derivative is just the rate of change of the function, right? And in particular, you're interested in the case where you are at xk. Okay, so the value of alpha is 0. So then what you're going to get is gradient of f of xk transpose dk. Okay, and this is what you're going to get at xk. So this is actually exactly what we said is the directional derivative. So here when we said any direction, we mean it's a unit direction. Okay, so now by this property of this Cauchy-Schwarz inequality, what you have is this term here, the gradient fxk transpose dk by norm dk. So that is bounded above by this norm. Okay, and the lowest value this can take is negative of this norm. Okay, so now when this happens, exactly when the dk value you take is gradient of f of xk. Okay, so if you don't remember this, you can go back and check the Cauchy-Schwarz. Okay, so Yeah, so that's why so these are, I mean, it's just coming as a result of taking the maximum value of this product, maximum and min values. Okay, so maximum occurs when you have decay is grad fxk, and the min happens when the decay, the direction is negative of the gradient. Okay, so that's why you have this, the maximum increase of f of x is at the gradient, is along the gradient, and negative gradient gives the direction of maximum decrease. Okay, so I hope this is clear to you all. You are all very quiet, so I don't know what's happening. Is this something you have already seen, so it's very boring, or it's not clear what's going on?
Clear.
It's clear? Okay. All right. So please ask, okay, if something is not clear, you don't have to feel shy and all. Okay, it's perfectly all right if you haven't understood and want to get it clarified. Okay, so okay, so now what are the facts we know so far that we formally describe what a descent direction is? Something of this form: P transpose gradient of f at xk is less than 0. And we also know this, that any direction, I mean, gradient is what gives you the maximum increase, and the negative one is giving you the maximum decrease. So now another useful point here is, so if you take any direction dk as, some matrix bk times the negative gradient, okay, and such that bk is a positive definite matrix, turns out this will also give you a descent direction at xk. Okay, so of course we must have that the gradient is not 0, because otherwise we already have reached a critical point, which may also be the minimum point. Okay, so when you have this direction, the idea is, the gradient is not 0 at that point. Okay, so does anybody know why this is true? If you take a positive definite matrix times the negative gradient, that is also going to be a descent direction at xk. So any thoughts why this is true? Or how can we show this?
Maybe the theta between this positive definite matrix and the negative gradient descent would be acute.
It's so what is a theta you're telling? Can you tell me? I'll just draw it here. So on one side you have what? So what are the two vectors you're talking about when you say the theta? Who answered? Raj,
I'm not sure about it. Yeah, not sure about the theta.
Pardon?
That's a matrix, so I'm not sure about it.
Okay, sure. So yeah, so this bk is a matrix, and bk times this gradient, that is a vector. Okay, so this is a vector, and yeah, so any thoughts on why this could be true?
Ma'am, the gradient into BK would be in the column space of BK. So essentially, because its lambdas are positive, it should sort of be in the same direction. So
So
there's
the
no
grade,
lambda inverting the direction in some sense.
can you
So
say
no,
that
I
again?
can.
So the
Ma'am, I don't know if it's correct, but it's because so BK has all eigenvalues positive. So
yes,
sort of anything I multiply into the eigenvector will be in the direction of the eigenvector. And bk times gradient would essentially be in the column space of bk, which is governed by the eigenvectors. So I
right.
can just say that they'll still be in the same direction.
Yeah, the idea that you have is kind of that's the kind of intuition, but you have to take care of some technicalities when you write the proof. Okay, so in essence, what you're trying to say is dk times gradient of fk, right? So I'll just say gradient fk. I mean, just for notational convenience, I'm just using this to denote the gradient at xk. Okay, so dk times gradient fk. This is the value you have to check. and you want to check whether this is less than 0. So is this less than 0 is the question you want to ask. Okay, so now dk is what? Minus bk times gradient fk times gradient fk. Okay, so this thing transpose gradient fk. So this is just nothing but minus gradient fk transpose bk transpose gradient fk. Okay, so now like what you said, this bk is a positive definite matrix, so it has all its eigenvalues as positive. So that's why you have all these terms are going to be greater than 0 always. Okay, so and there is this negative term here, so that's why this along with the negative sign, this is going to be less than 0. Okay, so this is the characterization of positive definite matrices, which says that any vector you take, x transpose bk transpose xk, that's going to be greater than 0. Okay, so yeah, so this is why this is indeed so dk transpose gradient fk is going to take a value less than 0. Okay, and that's why if you multiply a positive definite matrix, if you transform this gradient using this positive definite matrix, you will still have a descent direction. Okay, so is that clear? It's a simple proof, right? That's the idea should be clear. All good? Yes. Okay. 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 So now, so this gives you a handle on how to further design algorithms, right? So you have different choices. So any positive definite matrix you take, and if you multiply it with the negative gradient, you're going to get a descent direction. So based on that, there are different set of algorithms that people had come up with. So one is the most obvious thing, right? The steepest descent. So that is, you just take dk as negative gradient. So remember that was a direction which gave the maximum decrease. Okay, so that's equivalent to setting this bk, this positive definite matrix. You just take it as identity. Okay, so then whatever you get, that is also descent direction. Okay, so this is the one of the most popularly used descent directions, the steepest descent algorithm. Okay, so I think you will come across this in several places. Okay, even I think in your machine learning class, you might have already seen, or sometime in future you will see. Okay, so this is steepest descent. Now another choice is what is called the Newton direction. So here, so what you do is you just take this bk as the Hessian and the inverse of the Hessian. Okay, so the overall direction you are going to get now will be the Hessian you take inverse times the gradient of f of xk. Okay, so negative of this, right? Okay, so this is called the Newton direction. In fact, whatever you saw yesterday, the Newton-Raphson method, right? That is a special case in which you had, it was in one dimensions, but it was exactly this this kind of a descent direction. And even in higher dimensions, if you have to do, you instead of the second derivative, what you would do is the Hessian, right? So Hessian inverse. Okay, so this is also another popularly used method. And in fact, it's actually much faster. In many cases, it's faster than steepest descent. Okay, so you might be wondering like, okay, we already have steepest descent. So why do we need more directions? Okay, why not just use one algorithm? So the thing is like for different problems, the behavior of each of these algorithms is very different. Okay, so basically the convergence properties. So you may or may not, terminate quickly. So that's why there's a need to, think of different directions. And the Newton direction is usually like much faster, but in the sense that it requires fewer iterations for many problems. Okay, to finally converge to the optimum point. But the thing is that each step of the algorithm, you need to compute an inverse, right? A matrix inverse. And this is usually, it is polynomial time computable, but still it is an expensive operation. Okay, so because of this, there are some shortcomings of the Newton direction, where if you have like this is usually the case in machine learning algorithms, even deep learning, right? You have like lot of data, and so these matrices are going to be very huge, and computing this inverse is not going to be, it's a very expensive operation. Okay, so that's the reason now people try to propose other variants. Okay, they like this thing of having fewer iterations, but they don't like this thing of this inverse computation. So that's why some other variants. So one is this modified Newton direction, in which instead of taking the inverse at every point, taking the Hessian and inverse at every step, what you do is you just take the initial point, x naught. Okay, you take its Hessian and use that inverse at every step. Okay, so at every step you're going to compute this gradient. So dk is going to just be this one minus Hessian of the first point times grad fxk. Okay, so at every point, at every step, you will compute the gradient, but this inverse computation, you will just do it once at the beginning. Okay, so in that way, you're saving some effort. But again, so this is a heuristic. Okay, so we can never say what's going to happen, like whether it will really converge, or how long it will take, or whether it will really be a descent direction. Okay, so I mean, it will be a descent direction because this is positive definite, but whether this is the best thing to do, whether it will converge quickly, those things we don't know. Okay, but it's just some kind of a heuristic. Now another thing people do is they still want to make use of the second derivative at xk, but maybe don't take all the cross terms. So in terms of the Hessian, if you take you have these you have terms like this, right? Grad with respect to xi and xj in terms of different coordinates. So totally avoid taking these, so that what you get is a diagonal matrix. You only look at the dou square f by dou xi square. So you only look at the diagonal entries of the Hessian, and you just put everything else as zero. Okay, so the reason why this is useful is taking the inverse of this kind of a matrix is easy. So the inverse, what is the inverse of this sort of a matrix?
Inverse of the diagonals.
Inverse of the diagonals, right? So you just do 1 by d1k, 1 by d2k, and so on. So, 1 by this gradient value, sorry. Yeah, so d1k is going to be 1 by dou square f by dou xi square. Okay, so that's an easy computation. Okay, so this is called the diagonally scaled steepest descent. Okay, now there are other methods which try to, so these quasi-Newton methods, they try to build, they look at the Hessian inverse at every point itself, but instead of explicitly computing it, they try to approximate this value, the Hessian inverse, using some prior information. Like you have some of the points that you computed earlier, you try to make use of it to further approximate. So that is what quasi-Newton methods are. Now, there are also another set of algorithms like conjugate gradient, where also you have, you suitably design descent algorithms, I mean, descent directions accordingly. Okay, so so this is just a very quick introduction to these descent directions. So I just want you to, get a flavor of this. So if time permits later on, maybe we'll come back to some of these methods, things like quasi-Newton and maybe even conjugate gradient. Okay, so for now, I just want you to know that these are the several options that you could use to, design your algorithm, your optimization algorithm. Okay, so any questions till here? Any questions? Is this okay? Okay, am I audible? No questions. Okay. What about the others, Siddharth? Clear? Okay. Clear? Okay. 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 Okay, good. So, all right. So now this was about the choice of the descent directions. Okay. So now you remember, like, we had this xk plus 1 is xk plus alpha dk. Okay. So there were some other components that we had to choose. So we have done this now. Now the next thing is, how do you choose the step size? So alpha k. Okay. So, okay, so how would you do this? Now, what is again your criterion is you want to, f of xk plus alpha k dk. You've already fixed the dk. This is fixed. Okay, now you somehow one of these methods you choose and dk is fixed. And now you want to choose this. Okay, and the criterion is you want this function, which is evaluated here, to be as small as possible. So in some sense, you want to choose an alpha that minimizes this. So you want to choose the alpha k, which minimizes this function. Okay, so if you can do this exactly, if you can solve this minimization problem exactly, that is like the most ideal thing, right? So that is the best value of alpha you could put, given that dk is the direction you're going to take. Okay, so this in some sense, it is itself an optimization problem. Okay, but only thing is it's in one dimensions. It's in one dimension. So what you can do is, like, some of the methods we saw yesterday, that is something you could use. Now also, you could also try, like, since it's a simpler problem, maybe setting the gradient to 0, and then, I mean, using our necessary and sufficient conditions. That's also another way you can do. Another way you can set this value of alpha. Okay, but yeah, it depends on the function also, whether you're going to get closed form solutions or not. Okay, so this kind of way in which you try to find the exact value of alpha which minimizes this is called exact line search. Okay, so line search, perhaps because you're looking on a line, right? So this xk plus alpha dk, where alpha is the variable. Okay, so it's in some sense you're looking at a line and you're trying to find an alpha on that line. Okay, so yeah, so this is one way. Now, many times that also may not be feasible, like to finding this exact min. You might end up wasting a lot of time just to find one step. Okay, to find the step length itself, if you end up spending a lot of time, that is not acceptable, right? So there are other heuristics people use. So one is just use a constant step size. So alpha is some s. Okay, so this will, of course, you don't know whether this is a good thing to do, whether you're going to, whether you're finally going to descend or not. That's not clear. It is going to depend on this particular value of s. Okay, but if you have some prior idea about the function, and maybe that small step sizes are sufficient, so then you can just fix this as some s. So this are some things people do in practice. Now another thing is you take diminishing step sizes. In the sense, you initially start off with a big step, and then slowly you try to reduce it. So the idea is that initially you may be a bit far, but then as you make some progress, you're going to be closer to the optimum. So then you get more conservative. Okay, so an example of this is fixing this as 1 by k. So the alpha k, in the first step you take alpha as 1, next step you take it as half, 1/4, and so on. Okay, so this is one thing people do. So the only issue is sometimes for some problems in the initial stages, this one itself may be too big. Okay, you might like this other case that I mentioned earlier, where you have not even decreased. Okay, you've overshot the optimal, and then you're also increasing in the function value. So that can happen. Okay, so yeah, these are some issues that are there, but many times people try various such options, and then they choose what fits them well. Okay, so one thing here in these diminishing step sizes, this method, is that they also try to enforce this condition as true. So if you take the sequence of alpha k's, it diverges. The summation should diverge. So this is put in there just to ensure that you are also making some progress. Okay. Otherwise, the step sizes can become very small so that you don't make a move at all. Okay. So you don't want that to happen, and that's why this condition is also included. Okay. So that's about this method. Now, so these are all heuristics and they don't have any guarantees. Okay. Another thing that people do is something called inexact line search. Okay. So here, remember, like in the beginning, we saw some examples. Okay, of where you have large steps or sometimes you have very small steps. So the idea here is you ensure that you are not too small that that there's no progress. So alpha should be large enough that you make a progress, but also not too large that you cross the min point. So in some sense, what these kind of methods they use. So these Armijo's rule and Goldstein rule, those are some of the criteria. Okay, some of the rules they use to fix the alpha. So the crux of it is just that you've identified two regions like this. So this is the point where you are, the x case. Now you identify a first region. So perhaps it's a line that you draw, and when you make a progress, you want to exceed this point. So this is the point where this line touches the function, and you want a decrease which is better than this. So okay, something beyond this you want. Okay, so something after this. Okay, so anything in this range. So that's the first rule. Now another rule is you don't want to go too far so that you overshoot the optimal. So that is, perhaps you draw another line which is in terms of the slope, it is more than this line that you considered earlier. So you have this line here, and this is where it touches the function. Okay, now you want to be sure that you are within this. Okay, so one rule says that you should be in this region, the other rule says that you should be in this region. So what you take is the intersection of this. So this is the region that is suitable to be in. Okay, so your alpha should be such that the new point is somewhere here. Okay, so this is just to give you an intuition of what these rules say. So again, these rules, I maybe if we have time later on, we'll come back to it. Okay, for now, it's just important to understand that these are also like some heuristics which people use. Okay, because you don't want to spend too much time to find the best alpha. Okay, so any questions till this point? Any questions? Is this clear? You're all quiet. Am I talking to myself? Rohit, it's clear, or what is the... No questions. Okay. Okay. I hope you guys are all here and paying attention. So you should ask if something is unclear. I can also make mistakes. So stop me if something is not clear. Okay. So I think we are almost through for this class, but I just want to also spend a few minutes on the stopping criteria. Okay, so so we saw this thing, like we how to fix a direction, how to fix a step size. So now you keep doing these iterations. So at some point you've got to stop. Okay, so what could be a good stopping criteria, right? So any thoughts on this? When should we stop this algorithm, guys? Any thoughts on this?
The accuracy level is reached.
So the accuracy level, by that, what do you mean?
That something eta letter that we were considering.
Gradient is within a range of some
Yeah.
gradient is less than or epsilon or something.
Right. So something like this, right? The norm of the, sorry. So norm of the gradient. So if this is within some epsilon, okay, so you can stop here, right? So yeah, this is one possibility. Now, there are some other criterias also you can think of. Okay, so one is, you can do something like, if the function value doesn't change too much, okay, so then you can stop. So this is some kind of a tolerance you have on the gradient. Now, similar thing, you could have something like this. So f of xk, so f of xk minus f of xk plus 1. So if this is less than epsilon, you can stop. Okay, so this is one thing. Now, another condition is also the X case, right? The iterates that you're doing, that also you might end up stopping after some time. I mean, you may not make much progress there. So then that is also something you can do. Xk minus xk plus 1. So the norm of this, if it's less than some epsilon, that is also something people use. Okay. Now there are also other things that you can use something like the relative error. So instead of taking this difference in the functions, you can take the relative error. Okay. So how much you moved with respect to the previous step. Okay. So something like this. Okay. So if this is less than epsilon, you stop. So absolute value of this. But one thing that people do is adjust this instead with something of this form, max of 1 and f of xk. The reason being that, if these function values themselves are very small, then further dividing it by fxk makes it, you may never cross this epsilon range. So that's why you ensure that what you're dividing by is at least 1. Okay, so similar thing you can do with even the x case, right? Xk minus xk plus 1 by max of 1 and the norm of xk. So something like this you can do and ensure that that is, once it is within epsilon, then you can, stop. Okay, so yeah, so these are some of the stopping criteria that people use in practice. So I also wanted to give you an example. Maybe I think we are running short of time, so we'll do this in the next class. So is this clear? Whatever we did today, we were generally very quiet. Is it like afternoon after lunch and sleepy time? What's happening? Are things clear? No response? All clear? It's all clear. Okay. Okay. All right. So, yeah, I keep saying this. So please reach out in case some things are not clear or any issues at all. Please reach out to us. Okay. So with this, I will stop for today. So have a good weekend. All right. I'll see you on Tuesday. Okay. Thanks.
Thank you, ma'am.
Ma'am,
Yes, Siddharth.
I'm in the third criterion.
Mm-hmm.
When xk are changing, like,
Uh-huh.
so in that one, what if function is showing a lot of variation in that particular interval of x, and then we'll stop thinking that x's are not changing very much, but function is changing a lot.
Yeah. So it's not that you apply. I mean, you have to see like what works best for that function that you're changing. So sometimes you can also use a combination of these factors, right? So one thing is you can say both of these. So if you stop only as long as the functions are the change in function is less, as well as the x's don't change much, right? So that is also one thing. So uh, this criteria 3 that is there, it mainly caters to these functions which don't change so much. The change in function value is not much, but still there is no point in going on changing the x's. Okay, so yeah, so these are like different set of rules, like you have to choose them wisely depending on what function you're going to optimize. Okay, there's no one
But we
best.
don't know beforehand, right? Majority of the functions are very complex. So if we are not able to get explicit form, like y equal to x sort of form, that is not a very complex function. So how do we know that in that x range the f is varying that much?
Yeah, that is true actually. So one thing you possibly do is, try to mimic this function, like, try with some smaller dimensions. Okay, so usually the thing is, if these functions are, in higher dimensions, it becomes hard to even visualize. So one possibility is you just try on with lower dimensions and see how the function generally behaves. Okay, or that is one possibility. Then for some classes of functions, like for quadratic functions, you may have this kind of a behavior. Okay, for something like exponential functions, the behavior is different. So one thing you can do is spend some time, try to identify where, to if the function belongs to any of these well-known categories. Okay, and for some categories, some particular rules may be more appropriate. Okay, so yeah, there is really no one step to, there's no one golden formula to do this. It's you have to try out different tools. Or the other option, like, I remember doing something like, I tried one stopping criteria, and I was not very happy. It didn't seem like we reached an optimum. So then maybe we thought the issue may be the stopping criteria, try some other stopping criteria. So that's also something which people do, just try many of them and then just see which where you reach, and whether in one of these methods you're reaching a different point. Okay, so yeah.
Okay. Mhm.
Yeah.